Okay, assalamualaikum guys. Good morning, afternoon, evening. So this is part two of chapter 8 where we're doing some questions. So let's look at this first tutorial question by the way. So this question here states to determine the minimum force P. Okay, this is our force P here. We're pushing our crate up a plane, okay, as shown in this figure. The crate has a mass of 60 kg and the coefficient of static friction between the crate and the plane is 0.25. Okay, that's a given as a US already. So to find this minimum force P. Okay, so in order to solve this problem, allow me to draw a free body diagram. So let's draw a free body diagram here. Okay, and I'm gonna draw the crate. Okay, so this is our crate, and we're applying a force P on it. Okay, we're applying a force P. Okay, and the angle here is 30 degrees. Okay, so it's 30 degrees. All right, and what else? This crate also has a weight. Okay, don't forget it. So the weight of the crate is what? It's basically 60 kg times 9.81, right? Times 9.81 meters per second squared. So just 60 times 9.81 is 588.6. So it's 588.6 newtons. Okay. And of course, you'll have a component, right? This component here, which is W cos 30. Okay. Because the angle that it makes here actually is 30 degrees. And then you also have another component that's going down the slope as W sine 30 degrees. Okay. Here's the thing to note because we because the question was asking for the minimum force required to push the crate up. So this particular crate actually has a tendency to go up. So that means the friction will resist it from going up. So the friction will actually be downwards. Okay? And of course, there'll be normal force acting on the crate, and I will just label this as NR. Okay? And I will set the axis such that the positive x-axis is facing on the surface of the slope, whereas the positive y-axis is just going upwards on the slope itself. So one thing to note about this condition, because the question says the minimum force P required to push the crate up. So to push the crate up, the minimum force required, it's actually saying that the crate's about to move. Oh, okay, hold on. Yeah. So it's actually saying that the crate is about to move up. Okay, that's what it means. About to move up. So the frictional force that we have here, this frictional force is basically the maximum frictional force offered by the surface itself, which is equivalent to USN. And we already know our U is 0.25. I put NR, sorry, yeah, just to differentiate. Okay, NR. All right. So let's try to find this minimum force P. Oh, by the way, before I go on, actually, the angle that the P makes to the surface of the crate here is 30 degrees also, okay? It's also 30 degrees, so it's the same as the 30 degrees of the slope, okay? So yeah, so let's actually try to proceed and solve this problem. So using the equation of equilibrium, we know that the summation of Fy is equivalent to 0, okay? So for Fy, we know there's only two forces. One is the normal force, another is the component of weight, right? So minus W cosine 30 degrees equals to 0. So your NR is equivalent to W cosine 30 degrees. Okay, which is equivalent to 588.6 times cosine of 30, which is gonna give me 509.74. So 509.74 newtons. All right. So that's your normal force. All right. And of course, you can relate your normal force with the frictional force, right? Because the frictional force is the maximum frictional force, which is just 0.25 of the normal force itself. So in this case, your frictional force would be 0.25 nr, which would mean 0.25 times 509.74 would be 127.44 newtons. Okay, and upon finding that, then we actually proceed with the x direction. So from here, summation of fx equals to 0, right? So the forces that are important obviously is P, but we have to remember that our P is not in a line with the x-axis, so that's why you multiply cosine of 30. Okay, so we get the cosine component that is aligned with the x-axis. Oh wait, actually I made a very small mistake, because our P also has a component of 30 degrees aligned to the x-axis. It also has a y-axis as well, which I just realized. I completely forgot about that. So we also have a P. Oh, sorry, I thought it was a different color. We also have a P that is aligned to the y-axis. So that means to say I made a mistake there, but I realized it now. Okay, so we have to also minus. This is the sine component, yeah. So it's P sine 30 degrees. Okay, so in this case that would be minus P sine 30 degrees, which is equals to 0. Okay, and sine 30 is just half actually. So sine 30 we know is just half, so it's just gonna become half P, sorry, uh NR minus half P is equivalent to W cosine 30. So W cosine 30, W is already 588.6. So it's just 588.6 cosine of 30. So it's supposed to be 509. So it's 509.74. This is your first equation, okay? Okay, which I think I'll just probably leave it at there. Okay, let's call it as equation A. Okay. Then another thing to know is that we are doing if we're doing regards to the x-axis, which I just realized. So we need to say that if having the positive x-axis direction equals to 0, so we're left with P cosine of 30, all right, minus W sine 30, okay, minus W sine 30, minus F, okay, and this F is related to our NR, it's just 0.25 NR, so I'm going to write down there 0.25 NR, okay, which is the frictional force, F max. So we only have P cosine 30, W sine 30, and F. Yep, that would equal to 0. So we'll end up having negative 0.25 NR, okay, plus P cosine 30 is equivalent to W sine 30. So W we already know is 588.6. Sine 30, so we'll be having 294.3, so it would be 294.3. All right. So that is your equation B. Okay. So let's not confuse ourselves with 8 here. This is more of an equation B, but I'm gonna write it here itself here. Equation B. Okay, so we have two simultaneous equations. Okay, so we're two simultaneous equations, equation A and equation B. So we of course have two unknowns, nr and p, okay, are both equations. And since we have two unknowns and two equations, we can then proceed to solve the simultaneous equation. And I don't really have the space to solve the simultaneous equations actually, but if you solve the simultaneous equations, eventually you can be able to determine what's your nr and what is your p, okay? But we're more interested in p because the question wanted us to find for p. So if I compute the simultaneous equations, and you can compute them via a calculator also, there's a option for that, okay? And if you key in the values, all right, so your NR, you get 794.30 newtons, but your P is 569.12 newtons, okay? Which is gonna be about 569 newtons, okay? So it's 569 newtons for your P, and your NR is 794.30 newtons. But since you're interested in P, this is our final answer actually, okay, for the first part. This is the minimum force required to push the box upwards, okay? So number four is just basically a pair of simultaneous equations, so you can solve it on your own or you can use a calculator, okay, if you're running out of time. Okay, so yeah, let me just roll the eraser a little bit. That's a bit too much, isn't it? Okay, so yeah, okay, so that's for the first part. Now for the second part, if you look at the second part of the question, they ask us to determine the minimum force P required to hold the crate from sliding down the plane. Okay, from sliding down the plane, the crate also has the mass of 60 kilos and the coefficient is 0.25. So now in this case, what happens to a crate? Okay, so let's just answer for part B. So for part B, okay, what's happening is that the crate is no longer about to move up, it's about to go down. Okay, it's about to go down. So the crate will have a tendency of going downwards, right? And we want to find the force P required to hold the crate from sliding down the plane. So what does this mean? This means that everything else will remain the same, but your frictional force will change direction now. Now you'll have a tendency to go down. So the frictional force would actually go up. Okay? You'll have a tendency to go up. Okay? And yes, this would be a thing to consider of. So let's look back at our signs for the second part. So our frictional force will go up. The weight will stay the same, even its components cosine and sine. The components of P will still stay the same. The sine component, the cosine component. Okay, so your NR minus W cosine 30 minus P sine 30, okay, equals 0. Okay, this equation is the same. But for this equation, what's happened now is that it becomes a plus. So now your NR becomes a plus. Okay? And yeah, you get this answer. So if you solve the equation simultaneously now, your results will be different. Okay, for your N and for your P. Right? So in this case, it would be, so it will just be 0.25. So your N, okay, if you solve it simultaneously, your answer for your NR would be 593. So it would be 593.92, okay, 92 newtons, whereas your P would be 168. Okay, 0.38 newtons, or you can just simply write it as 168 newtons for three significant figures. Okay, so this is basically the minimum force required if the crate's about to slide down. Okay, with a tendency to go down, your frictional force will oppose that downward motion. Okay, that's the only thing. The rest will still stay the same. The rest of the forces, they'll have the same direction as it is. Your P, your W, of course, will be the same, right? Because weight's obviously pointed that way. Normal force. All right. So yeah. So that's for part B. Now for part C. Given that the crate is on a surface of 30 degrees from the horizontal shown in figure 7, what condition is required for the crate to be held in place if no external force is applied? Okay, so it says crates on a surface of 30 degrees from the horizontal. What condition is required for the crate to be held up in place, not sliding down, if no external force P is applied? What condition is required? So if the crate is not sliding down, okay, that means to say that and they said also that in our case, the there's no external force, meaning to say that P equals to zero. So if P equals to zero, okay, if P equals to zero, so part C, alright, so here is our part C, and then we say that P equals to zero. So we erase P out of the picture, yes? So we erase P out of the picture, so what condition must be in place? So the condition is that our weight, W sine 30, is to be equals to the frictional force F, right? So let me just erase all of these parts real quick. All right, to explain exactly what condition that we're looking for. Okay, so if we, of course, take our x-axis to be positive, so summation of fx equals to 0. So we know that in order to prevent the crate from going down, we know that W sine 30 has to be equivalent or minus the frictional force F is equals to 0. So that means our F is equals to W sine 30. Okay? So W sine 30 is 588.6. So 588.6. And times sine 30, we know that sine 30 is, half, right? So it's just half. So you multiply with 588.6. So it's 294.3. 294.3 newtons. Okay. And this is the frictional force. But then we have to check whether this frictional force is exceeding the maximum frictional force offered by the surface or not. Okay. So our F max is, we know it's 0.25 and R, right? Our normal force. And what we know about our normal force, okay, if we take the positive of y, summation Fy, to be equal to 0, okay, so that means we know that NR minus W cosine 30 is equal to 0, right? Cosine 30 degrees, yes? So your NR would be W cosine of 30 degrees, which is just, 588.6 cosine 30 degrees. Okay, so 588.6 cosine 30 degrees. So 509, so it would be 509.74. Okay, newtons. Okay, so I think this would be part 2. Sorry, this should be actually part 2, right? Okay, and this is part 3. So F max would be of course 0.25 times NR, which we've got earlier. So it's just 0.25 times 509.74, which is 127.44. So you see the maximum frictional force that can be offered by the surface is 127.44 newtons, right? And they said that what condition is required for the crate to be held in place, not sliding down. So it's clear that our frictional force that we need to keep it in place is far greater than F max. And this is a problem because if F is greater than F max, that means the crate is gonna slide down, right? And that's a problem. So what can we do to overcome this problem? What condition we can do? So of course, the ideal condition that we can do is to adjust our coefficient of friction, okay? We need to adjust the US, okay? So we need to say that we have to increase our US actually. Okay, we have to increase our US such that it can prevent the crate from sliding down. Okay, so how should I propose this value of US? It's quite simple, really. Okay, so if I erase this, all right, we know that F max. Okay, we erase all this. We know that um, you know, the maximum frictional force. Okay, F max divided by NR is equals to US, right? And yeah, we can also, okay, all right, is equals to US, okay? So that means 294.3 over 509.74 equals to our new US. So our US would be 294.3 over 509.74, which is 0.577. So it's 0.577. So if you have a US of 0.577, then the crate is very likely to stay in place. Okay? And how do we increase this coefficient of um, static friction? Of course, by increasing the roughness, right? The roughness of the surface itself. So the one condition is either we can increase the roughness. Another condition actually, if let's say they didn't mention the angle, let's say for example, the angle they didn't mention in this part of the question, then you can also play with the angle itself. Okay, you can also play with the angle itself, which will affect the um, roughness, okay, which will affect the roughness or the coefficient of, not roughness, sorry, will affect the coefficient of static friction, and this in turn will of course, allow the box to stay stationary. Okay, but again, since our case is that the angle's already fixed, so of course we just increase the roughness of the surface itself. At least make sure that the roughness surface is having a static friction, a coefficient of static friction of 0.577 or more, then the box itself will stay in place and will not move down. Okay, so yeah, that's basically the first question answered for you. So let's go to another question. Okay, so let's go to the second question. I'm gonna also make it a little bit small as well. Yeah. Oh, okay, hold up. It's not going small as I wanted it to go. Okay, why is that the case? Okay. Let me resize it a little bit first, yeah? Okay, great. So, no, it's okay, just stay there. Okay. So we have a block A in this figure, has a mass of 50 kg, alright, and is resting on a surface for which the US, the surface here's coefficient of static friction is 0.25. If the pair gets C, it's smooth, meaning to say there's no friction between it. Determine the greatest mass of the suspended cylinder D without causing motion, okay? Clearly state any assumption if you make, if there's any. Okay, so let's draw the free body diagram of this case, okay? So we're gonna draw a free body diagram. So this is our um cylinder, okay? So okay, this is our actually not cylinder, it's more of a box actually. Let me cancel this question. Okay. So yeah. Okay, this is our box A, block A, okay? And block A, we have a force, right, due to the tension of the cable itself, which is given to us as T, okay? And of course, the angles are given to us as 3, 4, and 5. All right, great. And let's see. It has a mass of 50 kg. So it has a mass, I think I'll just use green color. So mass of 50 kg. So therefore its weight is gonna be 50 times 9.81. So 50, 9.81. How much newtons is that? 490.05, so it's a 490.5 newtons. Okay, great. And what else also? We know the dimensions of block A, right? I think they've given it to us to be 0.4, 0.25, 0.3, so 0.4. So here is about 0.4 meters, 0.25, and 0.3 meters. Okay. 0.3 meters? Oh, no, no, okay. This supposedly is not 0.3. Actually, the cable here, I think I made a little bit of a mistake in my drawing. The cable is connected here. Okay? This is the tension itself of the cable. The angle is 3, 4, and 5, which is a Pythagorean triangle. And here is 0.3 meters. Okay. So we have some very useful information here, right? And the question is asking us, okay, to determine the greatest mass of suspended cylinder D. Okay, for suspended cylinder D, because this is, I just draw for block A. Yeah, this is actually for block A. For cylinder D, if you guys draw a free body diagram, actually, all right. The thing is, this is your tension, all right, and basically here is the weight of cylinder D. So the weight of cylinder D is equal to the tension. It's just simply the mass of cylinder D times G. Okay. So it is a free body diagram. So if we're able to find a tension, it is equivalent to the weight. You just divide it by the gravitational acceleration, which in this case we know is 9.81 meters per second squared, right? Which is right here, 9.81 meters per second squared. We can easily get our mass. Okay, so I'm gonna neglect the free body diagram for cylinder D right now. Okay, and let's see. They want to find um what is it? They want to find what? They wanted to find the greatest mass of the suspended cylinder without causing motion. Clearly state the assumption you make if there's any. Okay, so now we have two cases, right, for friction. The first assumption that we have here is that block A tips. The second assumption is if block A slips. Okay, whether block A tips or whether block A will slip. Oh, I forgot to add one more thing. The coefficient of static friction here is 0.25. Okay, that's important. So does it tip or does it slip? And of course, maybe it will tip or slip, all right? But which one will give us the greatest value of t? So you want the greatest value of t, okay? That's what the question really wants. Because once you get the greatest value of t, then you can easily find the mass of d, right? Okay, so let's take the assumption number one, where block A will tip. Okay, how do we do that if block A tips? Okay, so assumption number one, block A tips. Okay, so how do we do this? So first and foremost, of course, whenever we have a block that's on the surface, it will have a normal force. Okay, it will have a normal force. And of course, since we have the tension that's pulling the cable, right? So it has a tendency, the block has sort of this tendency to go in this direction. Okay, so therefore, I think I'll write this down as NR, yeah, just to make it clear. NR. You'll have a frictional force that will act opposite to it, right? You'll have a frictional force that will act in this direction. Okay, I'll be calling it as F. All right. So now the thing is, how are we going to find this value of t? Well, not to worry. If we set our x and y axis, okay, so x positive is going this way, y positive is going that way, okay, not to worry. So if we, take the summation of fx to be equals to 0, summation of fx equals to 0, because we have a Pythagoras triangle 3 to 5, so we know that 3 over 5 times t will give us the horizontal component of t, right? Will give us the horizontal component. And if we do 4 over 5, that's later for the y part, it would give us the vertical component, okay? So in this case, our horizontal component is negative 3 over 5 times t, okay? And we have the frictional force plus F, okay, equals 0. So our frictional force is just 3 over 5 T, okay? Our frictional force is just 3 over 5 T, okay? And that's all good. That's not a problem at all. Now for a summation of Fy, okay, for a summation of Fy, we have a bit of an interesting tale here. Okay, because our tension T has a vertical component. Okay, it has a vertical component, by the way, so we do have to consider that. So it would be 3 over 5, okay, 3 over 5 T, yeah, 3 over 5, sorry, 4 over 5 T, okay, you have 4 over 5 T, okay, uh minus, okay, no, plus NR, okay, and minus the weight, which our weight is obviously 490.5 equals to 0. So we'll end up having 4 over 5t plus nr is equivalent to 490.5. Okay, so yeah, so 4 over 5t plus nr is 490.5. Okay, I'm not causing motion. Okay, all right. So now what? Now, since we have two equations, there is one thing, because we know that block A might have this tendency to tip, right? So that's also a thing to consider about. Let me see. Oh wait, I think I messed up the numbers. It's supposed to be 4 and 3 here. My bad, sorry. So let me just erase that real quick. So it's supposed to be here 3, 4. So yeah, this is not so. Oh, sorry. Put a mistake here. So it's supposed to be. Okay. 4, 4, 3, 3. Okay. So that's what we got so far. And then now, if we take the summation of moments, okay, the summation of moments, um, to be equivalent to 0, okay, what we do know is that this F and this T, right? Of course, we're taking 4 or 5. They'll create a couple moment actually, causing the block to rotate in a counterclockwise direction. So it would just simply be 4 over. Actually, you know what? I think I'll have a better space if I write down elsewhere. Okay, let me write down here. So, okay. So we take the summation of moments, okay, where we take the counterclockwise to be equal to 0, okay. So we have what? 4 over 5 t times 0.3, okay. That is going in a very counterclockwise direction, right? And here's the thing that this is a distance of x, by the way, okay. And of course, this would be equivalent to the clockwise motion of, let's see, nr, okay, nr. Actually, hold up. No, I think, I think this would be a bit weird if we were to talk about the couple moment of these forces. I think we take the moment at a particular point here. Sorry, yeah. To be 0. Let's take it at this particular point, okay? Okay, I'll take this point O, okay? So we take the moment at point O to be 0, okay? And so that means that basically there is no moment caused by friction, right? But for nr, we do have a distance of x, okay? This distance of x, let's see. nr, okay? So this nr, by the way, it has a distance of x, let's say, between the point O itself, which is obviously causing it to tip, right? So in this case, uh, it's going in a counterclockwise direction. So we would have here nr times x, okay, that's going counterclockwise. And then, of course, we'll have the weight, which is 490.5, okay. And actually, the weight of the block is basically half, yeah? Half of 0.25. So it will be 0.25 meters divided by 2, okay? Going counterclockwise. And then our tension force, which is obviously, we have two components here. The horizontal component, which will obviously create a moment in the counterclockwise direction, whereas the vertical moment, it's a vertical component itself, will not create any moment with respect to O, so therefore it will just simply be um plus 4 over 5t times 0.3 equals to 0. Okay, so apparently I just realized we do have 4 unknowns, okay? For the first unknown we have here is our t. We do not know what our t is. Second unknown is our nr. And then we have our third unknown, which is our x. Okay, so how many unknowns is that? It's actually four unknowns, to be honest with you. But our f, we can express it in terms of t. So, that's already reduced it to like three unknowns already. So we have here three unknowns, actually. But still, it's made the equation a little bit more trickier now. Right? It's made the equation a little bit more tricky unless we hmm. Hmm. I realize this has got a little bit tougher. Let me read the question. Did I made it a bit more tougher or what? Block A has a mass of 50 kg, rests on the surface with U as 0.25. If the peg at C is smooth, no friction, determine the greatest mass of suspended cylinder D without causing motion. Clearly state the assumption that you make, if there is any. Well, the thing is, the assumption that we have is there's a possibility of block A to be sliding over the surface, right? That we could deny. But if there's also a possibility of block A tipping over the surface as well, it's able to tip over, okay? And that's something that we don't deny also. There's also a possibility of that happening, right? Block A could tip over, right? The surface. Okay, so there's also two possibilities of that happening. Either block A will start to move, right? And we don't want that to happen, okay? Or there's a possibility that if you have a block, it's very likely that it's gonna tip over as well. It's probably gonna fall over, right? So, what is it that I'm missing? If let's say we consider it tipping over, okay? Ah, okay, okay, okay. I think I got it. Hold up. Okay, I got it. So since you say we can make any assumptions, so let's assume that because block A is tipping over, right? So this particular x, yeah, that I mentioned earlier, this x will be equivalent to 0. Meaning to say, okay, what I'm trying to say here is that the distance between n r, okay, the distance between n r, okay, this distance between n r to the weight is actually equivalent to 0.25 divided by 2, which is equals to 0.125, okay, 0.125 meters. So the distance from NR to the point O becomes 0. So that means this X is no longer part of our problem. Our problem only deals with T, right? So we can erase this off the equation, right? Because that's the only thing that's going to be concerning us, right? We take the moment at point O, since NR is already at the edge of the block itself, right? So therefore, it's just 490.0.25 times 2, which is obviously going to cause a clockwise moment, and the tension in the cable is going to cause a counterclockwise moment, right? Equals to 0. So if we equate the equation together, so just simply 4 over 5 times 0.3 would give us 0.24t, so 0.24t, okay? Oh, this is minus, by the way. So therefore, once you bring it to the other side, it becomes positive. So it's 490.5 times 0.25, oh sorry, times 2, which would give us uh 61.3125. Okay, So that means that would lead your t to be equivalent if you divide it together, divide by 0.24, which would give you about 255. Okay, yeah. So it'd give you about uh 255.47 newtons. Okay, so if your T gives you 255.47 newtons, then all you have to do to find the mass, okay, is just simply T divided by 9.81. Okay, and this would give you about 255.47 divided by 9.81. Okay, which is about 26.04 kilograms. 26.04 kilograms. Okay, in this case. So just remember, whenever object tips, we must assume that this NR, okay, the normal reaction force, is already at the verge or at the edge of the body itself. Okay, we have to always assume that. So when you take the moment itself, then we already found out that, okay, yeah, because we already assumed the distance from NR to the weight of the body, it's 0.125 meters, which is basically half of this dimension. So therefore, the moment at point O will be 0, right, for NR. Just like for F, because F lies on point O, so there's no moment caused by the frictional force. Therefore, the only forces responsible for creating the moment are the weight and the tension itself, okay? So if the assumption is that block A tips, our mass at, sorry, I think I'll put it in yellow, sorry. Our mass at point D, okay, our mass for D, okay, would be 26.04 kilograms, okay? If we assume that it tips. The greatest mass suspended solidity, okay. Okay, so that's for the first assumption. Now, if we are considering the second assumption, okay, in this case, if we're considering the second assumption, which is when block A would slip, okay, so when block A would slip, so let me just remodel the diagram a little bit. So we are considering the second assumption where block A slips. That means to say that your F, your frictional force, is maximum frictional force, okay, which is gonna be, in this case, equivalent to 0.25 and R, okay? So, let me see, let me erase this part, by the way. Okay, so basically your NR would be lying along the same line as your center, right? Okay, so we use the equation of equilibrium, right? So first and foremost, your fx summation of fx equals to 0. So your summation of fx would just simply be 4 over 5t, which is negative, right? Plus f, okay, equals to 0, right? Yeah, we just put on negative 5t equals f equals to 0. So your f is equivalent to 4 over 5t. And we know that f is 0.25 nr, so you can say that 0.25 nr is equals to 4 over 5t. So the relationship is that your nr is equivalent, if you bring the 0.25 to the other side, yeah, if you bring it to the other side, it would just simply be 4 over 5 divided by 0.25, which is about 3.2t. Alright, so it's about 3.2t. Okay, so that's the case for fx. Then for the summation of your fy to be equal to 0, okay, so we have here 3 over 5t, okay, which is going upwards, plus your nr minus 490 0.5 is equals to 0. And we already know that NR is related to T, so it's just simply 3 over 5T plus 3.2T is equals to 490.5. Okay, so that means that 3 over 5 plus 3.2 is 3.8. Okay, so it's 3.8T is equals to 490.5. So therefore your T is equivalent to 490.5 divided by 3.8, which is about 129.07 newtons. 129.07 newtons. That means, of course, your mass, okay, is equivalent to T divided by G, alright, which is 9.81. So therefore 127.07 divided by 9.81 would be 12.95 kg. Okay, so this is the assumption if block A were to slip, which is basically 12.95 kg. That's basically the mass for cylinder D. Okay, and if block A were to tip, then the mass is assumed to be 26.04 kg. So which one is bigger? Because the question asked us that what is the greatest mass of suspended cylinder D without causing motion? So without causing any motion, meaning to say that uh, what is the larger mass here? So let's actually think a little bit through. If the mass of cylinder D happens to be 12.95 kilos, or maybe roughly about 13 kilos, okay? Well, I probably didn't write the approximation symbol quite nice. 13 kilos, okay? And here's probably about 26 kilos, okay? So you can see that it's roughly like a half, right? You're like, if let's say block A to slip, you just need 13 kilos, but if block A were to tip, you need about 26 kilos, okay? So the thing is, uh, if let's say you were to have 13 kilos, okay, 13 kilos on it, so 13 kilos you apply onto the block itself, the block will not move, the block will not slip. But there's a very good probability that this block will tip. This block will start to fall over, right? The block will start to fall over actually. But if, let's say, the mass of your block D, okay, is 26 kilos, okay, if the mass of your block D is 26 kilos, right? So what's gonna happen is that your block is not likely to it's not gonna tip at all. Okay, it's not gonna tip at all actually, meaning to say that block A won't like just fall over because again we have the rope, right? So if let's say block A it was a block D, I mean, if block D was about 26 kilos, right? Unsuspended, block A won't just fall over, right? Block A won't just like fall over actually. So that's what we're trying to avoid. So, since the question state the greatest mass of suspended cylinder without causing motion, ideally it'd be 26 kilograms, okay? It'll be 26 kilograms, not 13 kilograms, okay? Because it was 13 kilograms or lower, yeah, it might not cause the block to slip, but it would cause it to tip, okay? But actually, this actually brings a very important question. Hold up. What is the greatest mass of suspended cylinder D without causing motion? Actually, no, no, hold up. There's a thing here. There's a problem. I just realized. It will be this. Okay. Now, why am I saying this? It might be a bit weird because you might think 26 kilogram might be the answer. But here's the problem. Because all you need is 13 kilograms for the block to not move, right? Logically, 13 kilograms is the block you need not to move. okay? And if it was 13 kilograms, this block will it will not slip at all. Okay, it will not slip because you will have achieved or attained the maximum frictional force. And if the mass of the block D starts to become more than 13 kilograms, then the block will move. The block will start to slip. So actually block A would slip first before it tips. Okay? I don't know if I'm making any sense. Actually, it sounds very nonsensical at this point. But what I'm trying to say, okay, is that it will slip before tip. Okay, so it would slip first before tip. Okay, so that's the idea. It would slip first before it would tip. Okay, because if you only apply 13 kilos, that's already enough. That's the maximum with the greatest weight you can apply to the block before it slips, before it moves. And any mass that's greater than 13 kilos, any mass that's more than 13 kilos, it would have already slipped. It would have already moved. And the question strictly said without causing motion, right? So, therefore, this is your final answer, okay? No more debates. This is your final answer. Hopefully, this is clear. And if you guys feel that my answer doesn't make sense, then you can comment on it, and we can discuss in the comment section, or you can also contact me through other ways, and we can discuss, as well, right? But no, but the question here, it's posed in such a way that's tricky, right? It says greatest mass. I also got fooled by it, right? But eventually I came to my senses and realized, no, it has to not cause any kind of motion. Whether you're slipping, whether you're tipping, it should not cause any motion, right? So therefore, we notice that slip is very likely to happen first, followed by tip, right? So slip will come first before tip because it only takes 13 kilos. If more than 13 kilos, then yeah, the block will start to slip already. So therefore, 13 kilos is the maximum, or 12.95 actually, which we've calculated, is the maximum mass that we can put into block D to prevent block A from ever slipping. Okay? Yeah, so that's the idea. Okay? Alright, so hopefully it's clear. Let's go to the next question, or the last question of the day of the tutorial. Question 2 seemed pretty simple, but sometimes the thing about static questions is that the way how it's worded, it can be very confusing if you're not careful enough, like I was. So I also got a bit fooled, by the question. But yeah, that's how it is sometimes. We just have to be careful. Let's go to the last question of the day. Okay. So this is the last question of the day. Okay, let's look into it. Okay. The uniform crate shown in figure 5 has a mass of 160 kilogram. Assume the man exerts only horizontal force on the crate. Okay, great. If the coefficient of static friction between the crate and the floor is 0.2, and the smallest force by the man is to move the crate, is needed to be determined, what are two assumptions that can be made? Okay. So when the smallest force by the man move the crate needs to be determined, what are two assumptions that can be made? Okay. So for part A, it's pretty simple. Okay. If we want to draw the free body diagram of the crate itself, okay. So part A, and this is, for example, you moving the crate itself. Okay. So as you're moving the crate, okay, and maybe, for example, this is a person. He's moving the crate. All right. I think I should draw the person a bit more closer. All right. Okay. And he's pushing the crate. So there's only two things that can happen actually. The person is applying a force F or force P. So one, the crate could go forward, right? The first case is that the crate could go forward. In other words, it'll be a slip condition, right? It'll be a slip condition. The crate would move forward, of course, counteracting the frictional force. Or it could be a tip condition, right? The crate could actually fall down. Maybe the guy pushed the crate, and instead of moving forward, what actually happened is that He applied a force of P, and the crate started to tip over, right? Regardless of the frictional force that's applied on the crate itself, so it can tip over, right? So it's a tipping condition. So there's two assumptions: it'll either slip or it will tip. Okay, so that's for part A. Okay, moving to part B. If the coefficient of static friction between the crate and the floor is 0.2 and the smallest force by the man to move the crate to be determined, or sorry, part A already explained to it. Draw the free body diagram corresponding to each assumption, clearly label which free body diagram is based on each assumption. So, yeah, this is a free body diagram we drew, by the way. Of course, when you draw the actual free body diagram, please don't include the guy in it, okay? Uh, to draw it more appropriately, right? Okay, let me draw it more appropriately actually. So for slip condition, if we're talking about slip, yeah. So let's see what are the conditions that we can put here. Did they mention the condition of the guy? Okay, they did not mention the guy's condition. Okay, so we're gonna apply a force P. Okay, and the crate of course has a weight, which is mg. Okay, and then we have a normal force that's acting upwards, and R, and we'll have a frictional force here of F, which is equivalent to, in our case, is just equivalent to 0.2 and R, okay? Because it's a maximum frictional force, so therefore, this is the equation, F is equals to F max. Okay? So this would be the simple free body diagram for the slip condition, alright? And then for the tip condition, if we were to draw the free body diagram a bit more proper, okay, I'm gonna draw this a little bit more proper by the way, because this was not proper enough. So for tip condition, okay, if the boxes or the crate was about to tip over, how would it look like? So you have a force P, okay, you would have your friction F, okay, you'd have your weight mg, but your position for N would look like this, your NR. And the distance between your mg and your NR will be considered. In this case, it is half of 1.2, which is 0.6 meters, okay? Because here 0.6, here 0.6 meters. What else? 2.4, okay, so the whole box is 2.4 meters, okay? And it turns out that your P, okay, for a tip condition, I'm going to put it here, is 1.6 meters, okay? Okay, so this is for the case where the conditions are tip condition, okay? Right? So, yes. For slip, actually, you might be wondering why did I put the dimensions for slip? And you can put the dimensions if you want to. You can mention this as 2.4 meters if you want. You can mention this as, 0.6 meters. But for slip, usually, is simply very translational, okay? The thing about slip, guys, is it's very translational. It's a translational motion. Okay, translational meaning to say it's gonna usually only involve your summation of fx equals 0 and your summation of fy equals to 0. Whereas if it's tipping, you would have to involve your moment. Okay, so summation of moment equals to 0. It's rotational. It's more rotational actually. Okay, so rotational case. That's why for tip case, I added the dimensions for easier reference. But for slip case, I didn't really add the dimensions because it's mostly a translational case. It's just either moving in the X and Y. So I would say it's fairly simple. Whereas for tip, we have to worry about the crate rotating, right? So there's rotational motion being involved. Of course, there will be translational too. You have to consider your fx and fy, but As I said before, there's heavier emphasis on rotational motion, whereas for slip, the heavier emphasis is on translational motion. Okay, that's why I didn't put the dimensions because we don't really have to worry so much about the moment. Okay, whereas for tip, you do have to worry about the moment. Okay, so moving on to question B. For each assumption, determine the smallest force needed to move the crate. Okay, so to do so, let's assume the slip condition first. Okay, so I'm going to assume the slip condition first. All right, then we'll worry about the tip condition later. So in this case, if we assume the slip condition first, and we want to find the smallest value of the man with the pushing the box. All right, smallest force needed to move the crate. So in this case, how are we going to determine it? So first and foremost, okay, if we take our x, we take our y, okay, so we know that for summation of fy to be equal to 0, summation of fy to be equal to 0, we know that our nr minus the mg is equals to 0. Okay, because p is horizontal. So your nr is equals to mg. So mg here, the mass is referring to the mass of the crate itself. The mass is 160 kilograms. So it's basically 160 kilograms times 9.81. Okay, so 160 kilograms times 9.81, which would give me about 1,569.6 newtons. Okay, then we have to consider the summation of fx to be equal to 0. Okay, so in this case, that is your p minus f equals to 0. So that's p equals to f. And by the way, since our f equals to f max, so which is just simply 0.2 times the normal force. So our p is equal to 0.2 and r. So the smallest value of p that we get is simply 0.2 times 1569.6. So it's supposed to be 313.92 newtons. So it should be 314 newtons. Okay. So that's for the first assumption, slip assumption. So I'm going to erase this. Okay. And I'm going to write it here. So slip. Okay, for slip assumption, we know that our P is equals to 314 newtons. So now let's go for the second assumption, which is our tip, right? Our tip assumption. Because the question wants us to find which assumption is the correct one, right? To find the smallest force required to move the box. Okay. So we're drawing the same box again. Okay. And we have the weight, which is obviously just mg. And then we have the normal force here, and r, which is basically 0.6. Okay. Here 0.6. Here is 2.4. And of course, we have our frictional force here, F. Okay. And the thing is, okay, we don't have the force P, right, of the person itself. Okay. Force P of the person itself, which would be acting here. And the dimension between the force P to the ground is 1.6. That's the height of the guy himself. So it's about 1.6. Okay, these are all in meters, by the way, yeah? So these are all in meters. Okay? So for the case of slip, what we have to be alert of is, like I said, it's very rotational, right? It's all rotational. So it's if we take the moment at point O, okay, which I'm gonna probably put it right here. If we take a moment at point O, okay, so the moment caused by the normal and the frictional force is of no interest to us, right? Because once we take the moment at point O, the normal force is acting along the line of point O. So therefore there is no rotation. Okay, so in this case, actually wait, hold up. For this case, actually, I'd rather take the couple moment first because oh no, we assume that's gonna be here. Okay, fine, that's fine. So moment at point O. Okay, so in this case, um, what we can say is that if we take a moment at point O, the summation of m at point O equals to 0. Okay, so the only force responsible for the rotation is the weight, which will be going in a counterclockwise moment, which will be giving a counterclockwise direction. So in this case, it is uh, mg times 0.6, okay, going counterclockwise, and your p is going in a clockwise direction, right? It's going in a clockwise direction, so it becomes negative. So minus p times 1.6 is equals to 0. Okay, so therefore your p 1.6 is equals to mg 1.6. So m again is remember 160, g is 9.81, u is 0.6. So your p is what? So as a 160 times 9.81 times 0.6, it's 941.76. Oh my god, 76 over 1.6. So you divide that, so 941.76 divided by 1.6. That's 588. So 588.6 newtons, which is about 589 newtons. Okay? So this is the assumption that if we consider the tipping case, okay? This is for a tipping case. So I'm supposed to put 589. What is this supposed to be? 589 newtons, okay? So this is for the tipping case, okay? And the tipping case was 340 newtons. So now the question asked us, which assumption is the determine the smallest force need to move the crane. So part B. Okay, so slipping, you'll get 340 newtons. For tipping, you get 589 newtons. Now for part C, the question asks, based on the answers obtained part B, which assumption is the correct one? How is it being determined? So clearly, it will slip. Okay, so the slipping assumption is the correct one because the question is asking us to find the smallest force needed to move the crate, right? So of course, slip assumption is correct. So in our case, the slip assumption is correct. Okay, how is it correct? Because of course we know that 340 Newton is less than 589 Newton. Okay, we know that. Okay, and how is it being determined? So how do we know that the slipping assumption is correct, not the tipping assumption? Because the thing is, you see, this person himself, this person who's applying a force of P, and normally for a heavy crate, yeah, typically for a heavy crate, he's more likely to push the box forward, actually. From our logical understanding, he's more likely to push the box forward rather than tipping the box, actually, because he's not very likely to tip the box since you need a lot of force to just tip the box, at point O. Whereas if he wants to make the box move, he just needs to exert a force of 340 Newton or more, right? So by exerting a force of 340 newtons or more, he'll be able to move the box, okay? And if he can keep it less than 589 newtons, which I think shouldn't be a problem, if he can keep it within the range between, so if your P is between 314, okay, to 589, then he can move the crate or move the box, okay? He can move the box without tipping, without tipping. Okay, and if he exceeds 589 Newton or more, then of course he's going to tip the box, right? He's going to have a tendency to cause the box to rotate or to tip. But it's very unlikely that he will. So, yeah, therefore, this is the smallest force that he can actually achieve, in this sense. Okay? Determine the smallest weight of the man so he can move the crate. The coefficient of refraction between static friction between the shoes and the floor is 0.45. Then he can move the crate. Smallest weight of the man, so that he can move the crate. Okay. So now this is no longer okay, interesting. Smallest of the man so he can move the crate. So if he wants to move the crate, so okay, gotcha. So we're gonna do part D. Okay, let me raise the crate. So in this case, for the last part, okay, if you draw the free body diagram of the man himself, okay, so the man is applying a force. P is 314 Newton, okay, and positive X, positive Y, okay. So he is pushing, right? So this is the frictional force that's generated on the man himself. And in this case, it's assumed that the man is actually slipping past because the man is trying to move. He's not going to tip over, obviously, right? Otherwise, he cannot move the crate. So, because it's already mentioned the man can move the crate. So immediately we know that this F, we want to reach the maximum friction, okay? Which in this case is obviously 0.45 times NR, right? And we know that this man, there is obviously a normal force acting on him. Okay, there's obviously a normal force of NR acting on him, and of course, we're asked to find what is his weight. How heavy should he be, right? Which is basically equivalent to your NR. So I'm gonna erase this real quick. It's a pretty simple part of the calculation, but let's just do it together. Okay, so in this case, our summation of fx equals to 0. Uh, that means we know that P minus F is equals to 0. Our F is equals to P, which is 314 Newton. Okay. Then, of course, if we take our summation of Fy to be equal to 0, we know that his NR is equivalent minus W equals to 0. So we know that F is equals to F max or 0.45 NR. So you can say that NR is just simply F over 0.45, right? In other words, we can say NR is equals to W. And we know W equals to mg, so it's basically F over 0.45 is equals to mg. G is 9.81. We already have our F is 240 Newtons, so M is just simply 314 over 0.45 divided by 9.81. Okay, so if you compute, he should be at least about 71.1 kilograms, okay, for him to be able to move the crate. So we've come to the end of our tutorial actually. So this is tutorial part 2 for chapter 8. So I really hope that this is very helpful. I understand friction can be a bit tricky because you have to consider two cases, right? Whether you are, whether you're slipping or whether you are tipping, right? So which is happening first? It really depends on the question. But, you know, most cases I've seen, slipping is likely to happen over tipping, okay? But uh, just do remember mind if it's slipping, okay? If it's impending motion, just remember that your frictional force is always the maximum frictional force offered, which is obviously equals to the coefficient of static friction times the normal force. And if it's tipping, so just assume that in order for tipping to really happen, okay, of course your frictional force will not be equals to F max, okay? And in this case, make sure that your normal force, okay, is how do I say this? The distance between the normal force is within uh the maximum width of half of the maximum width of the body itself, okay? That's the idea with tipping. Normally we take B over 2, let's say if we're asked to find the smallest force applicable, right? Because that's the most likely case that will happen. But yeah, so hopefully this is clear. Hopefully it makes a bit of sense actually, right? Which cases you have to consider. And yeah, I hope this helps. Assalamu alaikum.